Today we are here with the module 1 of the chapter 2, that is magnetic effects of electric current. So let's begin this. So first of all, we have here Oersted experiment. What is Oersted experiment? Let's discuss. Alright, we have a circuit over here in which there is a key, a resistor, and a wire XY that we need to observe. Alright, and a magnetic compass is there, and this circuit is connected with a battery. Okay, when the switch is open, there is no deflection in the magnetic needle of the magnetic compass. Alright, so switch off, no deflection in the needle. This switch is off and there is no deflection in the magnetic needle. But as we turn this switch on, this magnetic needle will deflect like this. Alright, turn the switch on, magnetic needle deflects. Why does this happen? Alright, watch here. This is a magnetic compass in which there is a magnetic needle. A magnet can only be deflected when it comes nearby another magnet, but I cannot see any magnet over here, but I see a wire XY which is carrying the current. It means this current carrying wire is representing the properties of the magnet. Alright, and this current carrying wire is representing these properties. So we can say that a current carrying wire is associated with the magnetic field. That is, a current carrying conductor is associated with the magnetic field. This is the conclusion of Oersted experiment. Now move ahead. We have magnetic field. What is magnetic field? Let's discuss. Alright, we have this circuit over here again. Alright, and this time the switch is on. This time the switch is on, but I don't see any deflection in this magnetic needle of the magnetic compass. Why this happening? Why there is no deflection as the switch is on? Because there is a high gap between them, a large separation between them. That's why there is no deflection in the magnetic needle of the magnetic compass. But when this magnetic compass comes closer, then there will be a deflection in this needle like this. Here, when it comes closer, the needle deflects. Why this deflects? Because now it is in the region of attraction or repulsion of this current carrying wire, or we can say that this current carrying wire produces the magnetic property up to a certain region, and beyond that region it does not affect this magnetic compass. And but when this magnetic compass is in the region, is in the space occupied by this magnetic region, then it deflects the magnetic needle. So this region around this current carrying wire in which it shows the property of magnetism is called magnetic field. So we can say that the region around a current carrying conductor in which a magnetic needle deflects is called its magnetic field. Now let's talk more about magnetic field. Watch here. A magnet has two poles, north pole and south pole. Okay, when we bring two opposite poles nearby, a south pole when comes nearby a north pole of another magnet, then they attract each other. Opposite poles attract each other. Alright, but when two same poles come nearby, like a south pole come nearby another south pole, they repel each other. In the same way, when a north pole comes nearby another north pole, they repel each other. So why they are repelling each other? Because these magnets are producing the magnetic field around them, in which the another magnet is experiencing a kind of magnetic force of attraction or repulsion. So we can define this magnetic field in one more way, that is, the region around a magnet in which another magnet experiences a magnetic force of attraction or repulsion is called magnetic field. Moving ahead, we have magnetic field lines. Watch here. Here is a magnet, a north pole and a south pole, and we are watching these lines. These lines are magnetic field lines. And how to define them? These lines represent the direction of magnetic field at any point. So that's why we say them magnetic field lines. So how to define the magnetic field lines? Watch here. The line drawn at any point of the magnetic field that represents the direction of the magnetic field at that point is called magnetic field line. Now, there are some properties of these magnetic field lines. Watch here. Okay, here a magnet, and these are the magnetic field lines associated with this magnet, and some properties are there. So they are closed curves. You can see here they are closed curves. All right, the curves are not broken. These are closed curves. The next thing, they never cross each other. They will never cross each other. All right, they flow from north pole to south pole in air. In air means outside the magnet. Outside the magnet, the direction of the magnetic field lines is north to south, north pole to south pole, north pole to south pole, north pole to south pole, outside the magnet. Okay, now they flow from south pole to north pole inside the magnet. Watch here, inside the magnet, south to north, south to north, south to north. So outside the magnet, the direction of the magnetic field lines is from north to south, but inside the magnet, the direction is south to north, south to north. All right, moving ahead, we have magnetic field due to a current carrying conductor. So what will be the magnetic field due to a current carrying conductor? We will discuss. Watch here. Here is a conductor which is carrying a current I. We have to find out the magnetic field at a distance r from this wire. All right, this B is representing the magnetic field. The magnetic field is represented by B, capital B. All right, so this magnetic field depends upon this electric current as well as this distance. All right, the magnetic field will be directly proportional to the magnitude of the current. That is, the strength of magnetic field is directly proportional to the magnitude of current. That is B proportional I. And this magnetic field will be inversely proportional to the distance between the wire and the point of observation. So the strength of magnetic field at any point is inversely proportional to the distance of the point from the wire. That is B inversely proportional R. Now some more thing about this. Watch here. This is the direction of the electric current, and these are the magnetic field lines. All right, so these magnetic field lines are like circles around this current carrying conductor. So we can say that the magnetic field encircles the conductor. All right, and watch here, this is the plane of the conductor and this is the plane of the magnetic field lines. So we can say that it lies in a plane perpendicular to the conductor. This is the plane of the magnetic field lines and this is the plane of the conductor. That's why we say this and this are perpendicular to each other. Now what happens if we change the direction of the current? How does it affect? Watch here. Reversal in direction of current flow reverses the direction of magnetic field. Means if we reverse the direction of current flow, it will reverse the direction of magnetic field. Watch here. This is the current, this is the direction of the current, and this is the direction of magnetic field. When the current is upward, the magnetic field is like this, anti-clockwise. But when the current is downward, like this, when the current is downward, the direction of the magnetic field is this, means clockwise. So the reversal in direction of current flow reverses the direction of magnetic field. Now watch here. How to define the direction of the magnetic field due to a current carrying conductor? With the help of right hand thumb rule. So with the help of right hand thumb rule, we will define the direction of magnetic field due to a current carrying conductor. Watch here. This is a conductor which is carrying a current I, and this is the magnetic field. These are the magnetic field lines. Watch here. If the thumb represents the direction of the electric current, then wrapping of the fingers will represent the direction of the magnetic field. Means if the thumb of right hand represents the direction of electric current, then the wrapping of the fingers will represent the direction of magnetic field, and this is called right hand thumb rule. Now moving ahead, we have magnetic field due to a current carrying coil or solenoid. So watch here. Let's talk about solenoid. What is a solenoid? Watch here. We have converted a copper wire, an insulated copper wire, in form of a cylindrical spring like this, right? Or we can wrap it over a material like this. All right. Okay. When the solenoid is supplied a current like this is a solenoid. We have supplied a current to the solenoid. Then what happens? This supplied current produces a kind of magnetic field around this solenoid, inside the solenoid. So the south pole and the north pole are created. That's why we say that when a cylindrical coil of insulated copper wire is supplied with a current, then the magnetic field is produced, and this device is called a solenoid. So how we will define the solenoid? Like this: a cylindrical coil of copper wire acting as a magnet when carrying electric current is called a solenoid. So when we supply the electric current in this, then what happens? Then it represents itself as a magnet, and the north pole and the south poles are produced. So if we bring a magnet nearby this solenoid, what happens? Either it will attract the magnet or it will repel the magnet. So we will say that this solenoid is representing the magnetic properties. All right. Now watch here. We have given the current I, due to which the magnetic field is produced, and the length of the solenoid is L. So the strength of magnetic field inside the solenoid depends upon the following factors. All right. The magnetic field which is produced inside the solenoid. Watch here. Outside the solenoid, the magnetic field is not uniform because there is a variation in the number of magnetic field lines. Here, here, here. Watch here. Here the number of magnetic field lines are higher. Here, lesser in the higher region. And in the same way, watch here. The higher amount of magnetic field lines in the lesser region. Here, the same amount of magnetic field lines in the higher region. Means outside the solenoid, the magnetic field varies, but inside the solenoid, the magnetic field does not vary. Why? Because it has the constant number of magnetic field lines inside it, inside the solenoid. That's why inside the magnetic field does not vary. So we can say that the inside magnetic field of a solenoid is not varying. So we will analyze where the magnetic field is not varying, where the magnetic field is uniform. We cannot analyze here because it is varying. We can only analyze the constant magnetic field. So the strength of magnetic field inside a solenoid depends upon the following factors. And what are these factors? Let's watch. The number of turns. Higher the number of turns, higher the magnetic field inside the solenoid. And the magnitude of current. Okay, higher the supply of current, higher the magnitude of magnetic field inside the solenoid. If we supply a higher amount of current, the magnetic field will be produced in a higher amount. All right. And the next thing is nature of core material, and that core material which is very suitable is iron. What is this core material? We will discuss right now. Watch here. In case of electromagnet. So in case of electromagnet, we will discuss that core magnet. What is an electromagnet? Let's see. It is a part of the solenoid. All right. Let's see. Watch here. We have inserted a soft iron core inside the solenoid, where the magnetic field is constant, the magnetic field is uniform. We have inserted there a soft iron core. This. Then what happens when we insert a soft iron core inside a solenoid? This iron core gets magnetized. Means this will be acting like a magnet. All right. So this soft iron core will be acting like a magnet until the current is flowing through the solenoid. All right. So and the turns of the insulated copper wire are highly packed or tightly packed with the soft iron core, and these are the magnetic field lines due to the current flowing in the solenoid. So whenever we insert a soft iron core inside the solenoid, it gets magnetized, and that magnet which is produced hereby with the help of the solenoid is called an electromagnet. Getting my point? The magnet we are producing in this means, in what means, when we are inserting a soft iron core inside a solenoid, then this soft iron core is converted into a magnet which is called an electromagnet, and hereby we can produce the magnetic effects in a soft iron core with the help of a solenoid. Alright, so we can say that a soft piece of iron is placed inside the solenoid. When the current flows, a strong magnetic field is created which magnetizes the iron. The magnet so produced is called an electromagnet. So this magnet which is produced with the help of the solenoid is called an electromagnet. Alright, okay, and the supply of the current is defining the direction of the magnetic field lines. Alright, watch here. Here the north pole is and the south pole is here. If we change the direction of these terminals, alright, if we change the polarity of this battery or the cell, if we take this positive and negative sign, we change the polarity of this battery or the cell, we change this positive and negative sign, then what happens? This north and south pole will also change. Means if we shift these polarities, the south pole will come here and the north pole will come here. So by changing the direction of the current, we can change the direction of the poles, north and south, and it is like the right hand thumb rule. We can define these poles with the help of right hand thumb rule. We can define this north pole and this south pole with the help of the right hand thumb rule. Okay, so if we want to change the direction of the magnetic field, if we want to change these poles, these north and south poles, then we must change the direction of these terminals. We must interchange these terminals. We must change the polarity of the battery or the cell. So that's all for now. See you again. Thank you.